This is the booth lecture, and I would like to introduce Dr. Stuart Phillips from McMaster University. For those of you who don't know where McMaster is, it's in Hamilton, Ontario. He's a professor there. He's the associate chair of research. He's the director of the Physical Activity Center of Excellence. He is also the director of the McMaster Center for Nutrition, Exercise, and Health Research, and he's a Canada Research Chair Tier 1. His research interests include human protein, skeletal muscle, aging, as if I count it right, 238 peer-reviewed publications and age index of 127. He's the top 1% of all cited researchers in physiology and nutrition. 55,000 lifetime citations for his paper, close to 6,000 total citations to his publications in 2018 to 21. He was named the Clarivate's highly cited researchers list as being in the top 1%. So his research is funded by the Canadian Institute for Health Research, the National Science and Engineering Council of Canada, the Canadian Foundation for Innovation in the US, NIH, USDA, and several industrial partners. And the one trivia fact that I learned yesterday is we grew up in the same town.
But I went to the way cooler high school than Dr. Kennedy. Yeah. We were the snobs. It's true. It's true. Yeah.
No part of that town's poor.
No, it's true. That's true too. Yeah. Yeah.
So I would like to present this plaque to you for speaking here at the booth lecture.
That's
so thank
really
you.
great. Thank you very much. That's fantastic. Yeah. Oh, okay. Thanks. Great.
And I will let you go ahead. His talk is on the mechanisms of human exercise, skeletal muscle hypertrophy from the gym to the lab.
Well, thanks very much, Jill. It's a pleasure and an honor. I've known Dr. Booth, Frank, for 20 plus years, but it took me until now to actually know that W, there's a meaning to it. And who knew it was Weaver, Frank? I'd have guessed William, something else before, but Frank Weaver Booth Lectureship, and the plaque is that's really special. I've been reading Dr. Booth's papers since I was a master's student, which probably says as much about how long Frank's been in this game as me. And I cite his work a lot, and so it's an honor to be named to give this lecture, and I hope I can do it justice. Full disclosure, Frank, you were in Baltimore a week ago, so some of this is going to be a little bit of a redo. I don't have enough fresh material to completely redo the thing, but there's going to be a few new things in here, which I'll hopefully will please everybody. It sounds impressive when you stand up and you've got X number of papers and everything else like that. It's because of you people out here, these guys here. They're the reason why my job is as great as it is. They're the trainees. This is the lab over the years. These are some of the graduates, and they really do the work. I get to come to Columbia, Missouri, and it seems like, hey, Stu Phillips, the guy's great, and everything. And I'm like, these are the people that are great, and full hat tip to them. We spend a lot of time in my lab talking about models for strength and mostly hypertrophy. And, as a function of both internal and external variables, probably the majority of people focusing on what external variables could be manipulated in order to affect how much your muscle would grow. We tend to focus a lot on what internal variables would predict this. I don't know that it's a multiplicative function in here. We don't really know what the relationship is, but we spent probably, I'd say, the first 10 to 15 years of my career looking at external variables and trying to manipulate those to affect hypertrophy. And while it's not an outcome, we do appreciate the strength as a function of hypertrophy plus practice. And quite simply, I talk to a lot of people about, what it is to get the strongest you can be. And we concerned ourselves with that as a question for about 10 to 15 years of my career. And more these days, we've been interested in how the principles that we've learned with young individuals apply to older individuals or population who have somewhat of a mobility issue or could have a mobility issue in a few years. So this is a paper, this is Chang Lim, he's a postdoc in my lab that we recently published, where we tried to sort of give people through a graphical representation our idea of hypertrophy as a function of internal variables represented by the biggest red square. In other words, we think that they're the primary driver of this, this phenotype. And then the relative contribution of resistance exercise variables that you can manipulate, diet. We've never added sleep, but hat tip to people that have shown us that that's important. I wouldn't have added that probably about up to 5 years ago. And unfortunately for a lot of people, and this upsets a lot of people when I put supplements down here, because they believe it should be about the size of this red box. And we think it's a tiny little sort of sprinkle on top of the sundae, if that's the right analogy. But the internal variables are multiple. And we've spent some time trying to figure some of those out. I'm not going to talk as much to those today, but I will address some that we think we've had a pretty good run at, and probably only a few of them matter in our books anyway. So the first one we're going to talk about with hypertrophy is really around protein supplementation. And this is what I've spent a lot of my career looking at. I often get invited to give talks about, how big of a role protein plays in it. And after 25 years, I can tell you that I'm a little bit underwhelmed by the role that protein plays, which again tends to upset a lot of people because there's a multi-billion-dollar and billion-dollar industry around protein supplements. And so I'll sort of give you our take. Now, when you come from McMaster University, the first thing that you have to say at least one time in your presentation is evidence-based medicine, because we like to think that we're the home of evidence-based medicine. And so I'm going to use at least evidence-based science to answer the question of how protein supplementation affects hypertrophy. I know a lot of you maybe came to sort of watch me talk about muscle protein synthesis and breakdown and all kinds of pathways. And we talk about them a lot in this figure here. And I'm not going to do that, mainly because that's a whole nother talk. And I won't do that today, but I'm going to rely on a meta-analysis that we briefly did. And this is Everson Nunez. He's a postdoc in my lab. And we basically try to answer the question, does the higher protein intake through either dietary manipulation or protein supplementation augment muscle mass or improve muscle function? There's lots of different ways of doing that. It could be through normal foods or nutritional supplements. Most often it's sort of dairy source proteins, whey, milk proteins, sometimes casein, or it could be plant-based proteins as well, things like soy. There's a few studies with pea protein out there as well. So you do one of these big literature searches. You have a small army of graduate students looking through, somewhere around sort of 13 and 10,000 papers over here, which is a lot of work to do. And when you go through and take out all the duplicates and you screen these sorts of things, you can look and see the numbers here. It's a lot of work. And I think people have sort of were initially impressed with meta-analyses in this area, but I've become less so because, to be really honest with you, the rigor that it takes to do these and do them right it's a lot of work. It's really hard to do. So, full recognition of the amount of hours spent in doing this. In the end, you sift through all of this, you do all this work, and you come down to about 75 randomized controlled trials. And it represents about 2,300 people. That's a career if you were to spend studying that many people. So obviously that's why we do this type of methodology. And you can see that the protein supplementations varied from about 10 to 30 grams extra per day, and some between 30 to 50 grams extra per day. And we had a lunchtime chat about how much protein you think you can eat and everything. You can eat a ton of protein, and you will digest a lot of protein. The question is, how much can your body use? And I made the point to say that unlike carbohydrates and fats, there's a very finite capacity to use protein or amino acids. And every species that we know, from fish all the way up to mammals, has evolved a way of taking off nitrogen and getting rid of it. So it's essentially toxic if you eat too much of it. And when I say toxic, everybody goes, whoa. And by that, I mean, we don't like ammonia to accumulate in biological systems. So if we're mammals, we make urea. If we're birds, we make uric acid. If you're a fish, you just excrete ammonia through your gills. So, with that in mind, then, these are ridiculous forest plots. And so I just sort of summarize. You're like, you can see the diamond over, of course, I can't even see that. So let's just say that when you combine protein with resistance training, you do get a small additive effect. And it's about half a kilo. And, you translate that, it's about a pound. And, that's not a lot of extra muscle when you're sort of, looking at it in the grand scheme of things. And the point I try to make to people is this is a small effect. It's in the, what we call small effect size range. And remember that the methodologies that we use to assess the gain, and this is not muscle. This is lean mass that's derived usually from DEXA, but a variety of other methods. So it's really not muscle. And when people talk about this, I just remind them that probably maybe 2/3 of that, maybe half or even less, is actually muscle tissue. So, taking that into consideration. And then when we look at the effects in people under 65 versus over 65 years, you can see that we get an effect in the younger people. In fact, they're the ones that drive this overall effect. But there's no significant difference. It just touches on the zero line here for older individuals. And that's a sort of a hallmark, unfortunately, of aging, is that, protein supplementation and even exercise are a little bit less effective in an aging person because of something known as anabolic resistance, which is probably akin to insulin resistance in that there's just a relative sort of refractoriness to anabolic processes in aged tissue. And that could be, again, another talk unto itself. So from a functional standpoint, when we talk about, gains in lean mass, it's pretty small. When we talk about it from a dose response standpoint, it tends to happen only in the higher doses. We don't see it at lower doses, and we definitely don't see it when it's below 1.2 grams per kilo. And I think just to put that in some context, 0.8 grams per kilo per day is where the recommended dietary allowance is. So we're talking about intakes that are twice as the RDA. Now, we can go higher, we can go way higher, but the response completely tops out, at least in our minds. So, to summarize sort of some of the take-home points, it's great to have more muscle. But what does it mean? It means you're a little bit stronger. Again, it's driven for a large part by lower body strength gains, because those are the most commonly practiced lifts. You end up with these types of differences, about 4.5 kilos, 5.9, 9 kilos. If you're going to hop on the podium at the next Olympics, this might be important. For mere mortals, that's not really a big change. And again, I point out you need 2,300 odd individuals to detect these types of things. How much you bench? Yeah, you get about an extra 2 kilos. So if that's important to you, so be it. On physical and function changes, and this was interesting to us, it's a very small effect. And you can see that it just grazes this zero line, but it is significant, but it's not big. From a hand grip strength standpoint, which is sort of the most common measure of strength that's used in older individuals, we didn't see anything. So, the answer to the question of protein supplementation is, yep, it's sufficient and it appears necessary if you're talking about maximizing the effects. But remember that the effect isn't big compared to the gains made. So if you look at it from a sort of a dose response standpoint, what you end up concluding is that actually going to the gym and lifting weights gets you about 85 to almost 90% of the response. And the protein effect is an added thin slice on top, but it's very thin. And, again, I hasten to add 2,300 people to see these types of effects. So if you test 50 people, which would be a pretty big resistance training study, chances are you wouldn't pick up the effect in your individual study. That upsets a lot of people, but that's the way it is. And that's 25 years of my career. There it is summarized. It's not a big deal. So, okay, moving on. We took a run at this one mainly because, my training was as a biochemist. I wasn't trained as an exercise physiologist. I teach myself physiology. And, I spent a lot of time in the gym when I was a younger version of myself. I spent a lot more time talking to people in the gym. I found it a great place to meet other people. I won't say that's where I met my wife, but it might have been something related to the gym. And I spent a lot of time trying to impress people with lifting really heavy weights. And it hurt. And the older I got, it hurt more. And I thought, is this really the way we should be lifting weights all the time? And one of the things that drove our learning back when I was in sort of undergraduate and graduate school was this strength endurance continuum. If you wanted to be strong, you lifted loads that were close to your 1 RM. And it makes sense because if you want to get good at doing this, you should practice doing this. And if you wanted endurance, you lifted lighter loads and you did it for more repetitions. And the hypertrophy sweet spot, as it was known, is somewhere between 6 to 12 repetitions. And then you got very little hypertrophy out here and even less down here. And you can sort of see how things go. And when you learn about how muscles are recruited, you learn something called the size principle. And really what it says is, the harder you drive your muscle closer to fatigue, the more motor units you recruit, and you begin to tap into these type 2 fibers they're the ones that grow when you lift weights. And you definitely do it here. But we said, well, what if you come to this range and you're still lifting lighter weights, trying to drive it to the point of fatigue? Size principle said you should try and bring in those motor units. You should activate those fibers, and maybe that's enough. So where does this strength endurance continuum come from? We think it's largely based on, I don't want to say, this is maybe it's the study, because this paper has been cited over 800 times. But this really sort of drives the point home. There are 4 groups to control: a low rep, so high weight, intermediate rep, and high rep. And here's the strength, as you would expect. You're good at lifting heavy weights. The test is a 1 RM. So to get better at lifting heavy weights, you practice lifting heavy weights. And I know it seems self-evident. If any of you know anything about the football combine, if you want to do well in the combine, you train for the combine. You don't practice catching balls because they don't practice. That's not a skill in the combine. Doing repetition, 225, 40-yard dash, vertex jump, these sorts of things, that's what they do. So to get better and get better scores, that's what you train for. So you get better at lifting heavy weights when you practice lifting heavy weights, and you don't when you don't do that. So it seems self-evident, but it sort of fits with the whole strength endurance continuum. And then, I don't like to show numbers, but I'm going to use them here just to make the point. These are muscle fiber sizes. So low rep, you get bigger across the continuum of all the fiber types here. Intermediate rep, remember, this is the sweet spot in hypertrophy. You get the same response. Numerically, you get gains in the high rep group, but they're not statistically significant. And we thought, well, actually, we don't think this is the original or the origins of this study. It's actually a much older study that was conducted by this fellow. And this guy's name is Thomas DeLorme. If you know anything about resistance training, this guy's sort of and he was an army captain when he did these studies about soldiers coming back from World War II. And in 1946, he publishes Heavy Resistance Exercises. And I think that's one of the best titles of the paper we've got out there. And he said, basically, when we're talking about injuries of the trunk and the extremities, we would like to develop muscular power. Now, that was a misstatement on his. What he meant was muscular strength. But let's say, I put in brackets here, is the most important factor in restoring normal function. That's the origins, if you like, of modern rehabilitation. What should we do with people that have been through an injury and bring them back? And heavy resistance and low repetition exercise was better for developing muscular power. And we should do that before we do stationary biking or endurance-based exercise. So rather than attempt to develop endurance in atrophied, weakened muscle, we should restore muscle strength to normal and then build endurance by means of low resistance, high repetition. And that's almost word for word, although it's been sort of juggled around, the statement that accompanies the strength endurance continuum. So we thought we need to test this. So we did what we do, which is tracer studies to look at acute rates of muscle protein synthesis or muscle protein turnover. And we figured that at momentary muscular failure, you're going to drive all motor units, regardless of the load used. So some of you might recognize this guy. That's Nick Bird. He was a PhD student in our lab at the time when he did this. And we had 3 conditions: 90% of 1 RM to failure, so a really heavy weight; 30% of 1 RM to match the external work of the condition, so multiply the load times the repetition; or 30% of 1 RM to failure. Okay. If you've lifted 90% to fail, you'll sort of recognize, I'll use the knee extension because that's what we use, is that you get to a point that the load slams down. You can't generate the force. 30% of 1 RM to failure is, I call it, the sewing machine phenomenon, because your leg's doing this sort of thing, but it's still failure. So you're reaching fatigue here and fatigue here. Different mechanisms, I certainly agree. But the point would be is that you're driving things to fatigue here and here. You're not here, because you can always do more work here. That's just the way the system works. So these are the rates of mixed muscle protein synthesis. We're making new proteins at 90%, and yet it's not statistically significantly different at 30% in the fail group, lower in the work match group. And these are the myofibrillar or force generating proteins pulled out of this fraction. You can see the same type of stimulation here, but at 24 hours post exercise, the 30 fail group looks even a little bit better. So the conclusion was low load, high volume resistance exercise is more effective at inducing acute muscle anabolism than even high load. So that really upset a lot of people. So we take peer review seriously. So we went to social media, which of course is their mental giants out there. And it's a good thing that these people don't review our papers. And I'll say that because it's pretty damn hard to impress people on social media with science. I'll tell you that. So this is what we heard from Twitter and Facebook. This is just muscle protein synthesis and not hypertrophy. Correct. Well done. Who lifts at 30%? You're not going to get strong that way. I'm like, good point. Maybe we should test that. So this is Cam Mitchell. He was a PhD student in my lab, and we basically asked, do the acute results we observed previously result with longer term training adaptations? So we did 30% of 1 RM to fatigue, and we reasoned that it should result in muscle hypertrophy, at least based on, if protein synthesis is correct, equivalent to that with heavy loads. And we compared it to 80%, which is closer to the sweet spot at that 6 to 12 repetition range. You do all the fancy measures, you take the MRI, you spend a lot of money because we wanted to do it definitively. We did cross-sectional area fibers, and this is what you end up with. 30% at 3 sets, 80% at 3 sets, exactly the same. And somebody said, what's the effect size here? I'm like, dude, it's tiny. Let's just say when P equals 0.85, it's pretty small. You would need 8 million subjects to detect the slight difference here. So, anyway, I digress. I just said, let's say it's trivial. Okay, so there's really no difference. But here's the interesting part. When you practice a task, and if it's the 1 RM here, at 80%, when you're lifting, you're only ever 20% away from that 1 RM. So look, you get better at doing 1 RMs. At 30%, you're 70% away, so you don't get as good. When you let everybody practice or let everybody test their strength with an unpracticed task, and this is isometric peak torque, everybody gets as strong. So this is a practice phenomenon. It's not anything specific to the type of hypertrophy you get. The amount of myofibrillar protein is exactly the same. So this to me is, sort of the definitive answer to, do you get as strong? Yeah, when you get an unpracticed task, everybody gets the same strength gain. When you get a practice task, of course you get better at doing that. Practice the combine, you get better at the combine. So we said, in accordance with our previous acute measures, protein synthetic rates, a lower load lifted to failure resulted in similar hypertrophy as a heavy load. Again, we got the paper published. It's been cited a lot. Facebook, Twitter. This was a unilateral design. Who cares? Like, we use one leg to do one condition, one leg to do the other. And I'm like, yeah, okay. These were untrained subjects, and they respond to everything. It's a popular notion that if you're untrained, you have some unlimited potential. And this, I learned a new word. These are called noob gains. So this is noob for newbie, and gains with the well, you say Z down here or Z. And honestly, I said noob gains, and my oldest son at the time, he wasn't quite as old as he is now. I'm like, what does that mean? He goes, noob, Dad, like new, like a new person. I'm like, oh, like a novice. He goes, yeah, like novice, you know? And then I'm like, gains. And he's like, yeah, so that's the S, the Z replaces the S. I'm like, got it. And I'm like, thanks, man. I'm like, you know, looking for the company, he just rolls his eyes and walks away, you know? So you try and be cool, but not really. So lifting at 30%, you don't get as strong. So who cares? And that's a good point. So we kind of wanted to design a study that would put the whole issue to rest. So we took trained participants, not noobs. So these were pretty well-trained people. We used a non-unilateral design. So we trained, it was a between group design. You guys understand human physiology. This is a crappy design. You got to use a lot of people because now you've got between person variabilities, but you want to be able to power it enough. So we tested 25 people per group. That's a big study in the resistance training world. We basically said, you know what, we're going to try and make people as strong as possible using a lower load. So we're going to give them a chance to practice the 1RM test every 3 weeks. Okay, not all the time, but every 3 weeks, they're going to get a 1RM test. And I said to the students involved, look, we're never going to please everyone, but this hopefully will close the chapter. So Sarah Kawa and Rob Morton, 2 master's students at the time with 50 people and individual supervision of training. You can't do it with 1 student. So they teamed up. We matched people for strength and lean mass. We trained using low rep or heavy weights or high rep or light weights. And instead of saying a % of 1RM, we said, you know, at the heavy weights, we want you to fatigue in that sweet spot for hypertrophy. And at the light weights, you know, the high repetition, we want you to fatigue in this type of range. So we did everything. They did bench press, they did shoulder press, they did pull downs, leg press, etc. We tested them every 3 weeks. We took biopsies, we did DEX, so we made hormonal measurements, we did everything. And I thought this is going to be the definitive study, and we'll finally stamp our mark, and load doesn't make a big difference. Sorry for so these box and whisker plots show you the top subject, the bottom subject, 25th and 75th percentile, median and mean. And that's the interquartile range of the high rep, so low load, or low rep, high load. I know it seems backwards, but and no difference. This is whole body lean mass, no difference. Fiber types, everybody hypertrophies to the same degree. No difference between the 2 groups. Impressively, everybody got stronger. Everybody got stronger in knee extension. Everybody got stronger in bench press. A small advantage to the low repetition of the high load group, which we think was a practice phenomenon again, because everybody knows you're only strong if you can bench more. Okay, so everybody practices bench. And shoulder press. And so, you know, everybody got the same degree of strong. The biggest criticism, again, from the social media world was these really aren't trained people. Now, my bench used to be pretty good, but anybody can translate 100 kilos, so 220 pounds. I'm like, they seem pretty trained to me. Or, you know, like a 380-pound leg press, or kilo leg press. So, you know, around 800 pounds, like, you know, they're pretty trained. Anyway, they were big guys, I'd tell you that. So let's just say when we sort of got to the end of this, we said, you know what? There are no differences in the increase in lean mass, no differences in muscle fiber cross-sectional area, no differences in gains between fiber types, no differences in strength with the exception of a small difference with bench press. We think that that's what the strength endurance, like hypertrophy exists along the whole continuum, so long as you go to muscular failure. So the debate rages on, but nonetheless, meta-analyses done by a number of other people have sort of backed us up on this one. So we're pretty confident we got this one right. Does all this really matter? I could give you an evidence-based answer. I'm not going to do that today, but let's just say meta-analyses have backed this up a number of times. High load, low load, it doesn't matter. So you want to lift weights, lift whatever you like. Now, people go, oh, well, how low can you go? And I said, well, like 30% of one repetition max, 20%. You can do 30 repetitions in these types of ranges. It's true. If I were to do arm curls with this controller, I'm not going to get bigger. But, 5 times that controller, you'll be okay. Rises in anabolic hormones are the last thing I'm going to talk about in this area, and I'm going to switch gears a little bit. Well established for years and years, you would expose someone to a stressful stimulus. It could be running 400-meter repeats. It could be lifting heavy weights. It could be clashing cymbals behind somebody's leg and exposing them to loud music. You get a rise in stress hormones. There's a generalized stress response that includes anabolic hormones. So by anabolic, I mean testosterone, which everybody, and I read it as a young man, drove everything. And if you didn't have the T, like you weren't going to get bigger. So the greater the rise, post-exercise rise in anabolic hormones, the bigger you were going to get. And for a lot of years, I was like, I wonder how much testosterone I have, because that's the key. And but part that sort of caused me to question that is I would look around the gym, and back when I was a young guy, there weren't too many women who lifted weights. There are more now, but some of them seem to get bigger. And I learned in endocrinology that they have tenfold less testosterone than men. So what's driving their hypertrophy? And somebody goes, oh, it's growth hormone. And I thought, growth hormone? Well, okay, maybe that's true. Or IGF-1, insulin-like growth factor. So we set out to test this one. The first thing we did was we just trained one leg, because that's a small muscle mass. You don't get a big change in these anabolic hormones, and yet you can get hypertrophy. So this is Sarah Wilkinson. She was actually my first PhD student, and she's a professor now. So there is life after, a PhD. And you get hypertrophy only in the trained leg, and nothing happens in the opposite leg. So here's fiber area, muscle cross-sectional area by MRI, without any changes in the T, the free T, luteinizing hormone, sex hormone binding globulin. Everybody said, well, cortisol is the anti-T, or it's just, if cortisol goes up, everything goes to hell in a handbasket. And we said, well, it doesn't change. And there's the testosterone to cortisol ratio, which a lot of people used. So we said, clearly, anabolic hormone rises are not necessary, because we can get hypertrophy without them. So are they sufficient? And if we get more of it, do you get more muscular growth? So we set up this paradigm. And if you're a young man and you read, the authoritative verses in Muscle and Fitness and Flex magazine, which are full of routines to show you that you never train your biceps before you train your legs. You always train your biceps, the small muscles, after you've done a big leg workout, because you get jacked more, because these drive up anabolic hormones, and then you bathe these small muscles in anabolic hormone. I know everybody laughs, and I'm like, I read that stuff as a young man underneath my covers with a flashlight. And I was like, yeah, I want to get, I just do a big leg workout. Then I'd be sitting there like this, and I was like, what's happening? Like, and you see me and people look at me and they go, you lift weights. I'm like, I've lifted weights since I was about 10 years old. Then something's wrong, right? So we said, well, we're just going to do one like bicep curl workout, tiny muscle, no big anabolic hormone rise. And we're going to exercise this one just like all the books and the magazines say, a big workout, and we're going to lift weights, afterwards, and bathing this arm in anabolic hormones. So you should be able to see these guys who come in one arm like this and one arm out here, it's so big, right? So we did that. And this is Dan West, and he did a really great job. His whole thesis was essentially bashing away at this hypothesis. And you can see that here's the high hormone condition. Here's testosterone, we get the rise, and here's the low hormone, or just the arm itself. So we did the first thing. We took bicep biopsies, which are a ton of fun to do. And we didn't get any change in muscle protein synthesis that was different between the two arms. What's the effect size? It's tiny, and actually it favors the low hormone condition. It's always good to, push back on some of the popular. So we thought, well, that's the end of that. You don't make more. It's thick. And clearly, everybody's like, well, that's just muscle protein synthesis. So we said, well, okay, we're going to do a training study. We're going to use our arm only and our arm plus leg condition here, and we'll measure the cross-sectional area of our biceps. We'll take muscle biopsies and look at this. So this is the area under the curve of testosterone in the arm only. You can see really small compared to the arm and leg early on in training and later on in training. So you do get a reduction in the stress response, but importantly, you're getting a difference between the two conditions that's pretty pronounced. Do all of that, and the change in the elbow flexor, so the bicep cross-sectional area, arm and leg, arm only, exactly the greater maybe in the arm only. So we thought, well, how much more do we need to do? This is surely the definitive study that has convinced people post-exercise anabolic hormone rises are not necessary, and they're not even sufficient. But again, no big deal, man. That was unilateral. Hormones not that high. What about strength? What about what so-called real world kind of gains with his head? But clearly, like this fellow right here, what's going on? So what we thought was, well, we're not going to do another training study. That's ridiculous. So we dipped back into the freezer and we used basically a model of individual variability. So here's pre-training guy. I should mention this. We're doing studies in women, and it works in women too. And they don't have like near as much testosterone, and they have about the same amount of growth hormone. And we can go on and on and on, but bear with me. So untrained guy turns into a trained guy, but he's blue, and he's a hard gainer. So this guy, that's the technical term. He doesn't gain any muscle. He works really hard, but he just sort of stays the same. He gets stronger, but he doesn't get bigger. Or you are that guy. And this is, that's the extent of my art capability. And there you go. So, keep an eye on blue guy and red guy here. This is a study that we pulled out of the freezer. We had 54 participants in here, so a big sample. And we had a few guys that are down at the bottom here, and we had a guy up at the top. And so I want to just keep an eye on, there's a hard gainer, and I remember this guy actually, he was editor of the newspaper. And I said, what sports do you do? Like, nothing. And, I work on a farm. And I'm like, oh, farm. And he goes, you should see my twin brothers. I'm like, get them in quickly. Take some muscle biopsies. So there's a 78-fold difference between this guy gained 100 grams. This guy gained 7.8 kilos of lean mass. It doesn't matter if that's muscle or not. This guy got huge. This guy just got a little stronger. Not that he worked any less hard than this guy here, just the right genes, at least we thought at the time. So there's blue guy and there's red guy, and here's the area under the curve of his free testosterone response. And you can see, I don't need to explain it to anybody here, the big free testosterone guys were kind of in the middle. Didn't really make a difference where you were. I could put up growth hormone, I could put up total testosterone, I could put up. The only hormone that was predictive of gains was cortisol, which is apparently catabolic. So figure that one. There's growth hormone, and blue guy was actually up in the higher end, but you can see that there's no relationship there. So the acute post-exercise rise in systemic testosterone, growth hormone, or IGF-1, they're neither sufficient nor are they necessary for stimulating rises in muscle protein synthesis, gains in lean mass, or in any way affecting any of the anabolic responses. So, we've got to this point where I think, hopefully I've convinced you that protein is important, but the effect is small. So when people ask me about, well, what about plant protein? What about 5 meals a day versus 6 meals a day? My answer is the effect is smaller and buried inside this effect. It's really about how much protein you eat. And as long as you're getting somewhere at about 1.6, you're probably doing pretty well. Load, Heavier weights are sufficient, but clearly they're not necessary for inducing hypertrophy and gains in strength. Strength is a function of practice. You want to lift big, heavy things and get really strong, practice lifting big, heavy things. It's an easy message. Finally, hormones. The acute rise post-exercise anabolic hormones is neither sufficient or is it necessary for the induction of hypertrophy. The work that we're doing now in women is, again, recapitulating that exact hypothesis. There's a phenomenon in women where a few people that are out there are sort of telling women that there are differences between certain phases of their menstrual cycle. And again, not to be too much of a spoiler, but that's not panning out either. So lift weights, get strong. It matters not when you lift. Your hormone response, not a big deal. Relatively speaking, women gain the same amount of muscle as men. Boys and girls, when puberty hits, that's when they diverge. After that, men and women lift weights, they all get about the same gains. In fact, women gain, relatively speaking, a little bit more, and they get stronger. Ooh. So what does affect hypertrophy? Not to belabor the point, but the answers here will be relatively short, and then I'm going to shift gears a little bit at the end. Resistance training variables. The popular notion is if you're not growing or getting bigger, you need to change your program. Tough question to answer. I got two graduate students, that's John McLeod and Brad Courier, and they're doing what's called a network meta-analysis. So they're trying to construct this node right here, or this, I guess, framework right here that you can see, the strength of the line is the number of studies that compare control groups to low load and high load and everything. And then when you construct this, you can begin to join nodes that actually aren't joined. In other words, you can create studies using sort of a machine language type network that haven't actually been done. So you teach the model how to make the type of comparisons and it fills in the lines that are missing. That is 118 RCTs, 3,348 people, 50% women, I'm pleased to say. That is strength, and this one is hypertrophy. So we get it's the other way around. This is hypertrophy, this is strength. Again, we did pretty well when we looked at all the studies. This was a ton of work. This was a pandemic project when we couldn't get into the lab, and these guys they're probably regretting taking it on because it was a lot more work than we thought. Soon to be hopefully submitted to a journal near you. When we talk about some of these other variables here, Chang and a lot of other postdocs in my lab, James McHenry, Everson Nunez, are trying to look at these sorts of things: mechanotransduction, mTOR signaling, ribosome biogenesis. And when it comes to transcriptomic responses, I'll just highlight one study of which I'm particularly proud, not the least of which is that it completely outstripped my knowledge, and it was the student that in the end became the teacher. It does happen, okay? It does happen. This is a great collaboration that we were involved. This is Mike Roberts. He's down at the University of Alabama, Birmingham. That's Chris Van. He was a PhD student with Mike. He's now a postdoc with Bill Krause at Duke. And we looked at genes. Everybody said, what's in your genes? And the answer is, I think that's true to some extent, the genomic background that you have. So blame mom and dad for just about everything. It's what kids do. No, that's kind of jaded, but there you go. I don't know that there's enough variability in SNPs that can account for a very complex phenotype. And when we sort of did, it's not really a GWAS type study, but it's GWAS-ish. We combined data sets. We came up with, I think it was about 120 individuals. And we came up with gene variant that you can see there we go, right here, that was actually in the intron variant of this zinc finger protein, that if you were homozygous TT, you were a lower responder. If you were heterozygous, you were sort of in the middle. Homozygous, you were up towards the upper end. For fiber cross-sectional area, type 1 fiber cross-sectional area, 2 fiber cross-sectional area. And interestingly enough, and whether this plays out, I'm not really sure, but also for satellite cell responses as well. So getting down to sort of some of the genotype scores that we think are important. And it's not the usual suspect in terms of genes that are supposed to, and when I say usual subjects, I mean direct to consumer tests say, if you have this genotype, you're a big responder, and not in our hands. So I can't really explain the discrepancy. This is Tanner Stokes. This is the fellow that I'm telling you about that he did a pretty cool study. We came up with this, what we call HIPAT model. In other words, we've got one leg doing resistance exercise, one leg doing immobilization. You don't need to immobilize a leg for 10 weeks, but you need to lift weights for 10 weeks to get the gains in one direction that you lose in two. So it takes 5 times longer to gain than it does to lose, unfortunately. And what he did was use this within-person design to generate a gene signature for hypertrophy using this interperson model that we then compared against a transcriptomic data set that we had for 100 individuals. We did a network analysis. We used machine learning to create a gene signature which would predict the variability in this response. And we get up to about 70%. When we did that, we basically went through, so these are the other cohorts that we used. And so it's sort of a meta-analytic based validation. And then we looked at these protein-protein interactions with sort of gene mapping here and network analysis. And finally, what we did, so we got to this point, and I sort of thought, you know what, this is pretty cool. We've got this gene signature. It's created in this small cohort here, but we validated against a new cohort. We submitted it to a journal, which shall remain nameless, but the initials are Cell Metabolism. And we got rejected. It took 37 hours to reject the paper. I think that's pretty quick. And they said, but you can submit to our sister journal, which is sort of like the, over there, Cell Reports. I thought, well, that's got a pretty good impact factor. I think this work deserves some highlighting. We got there, and the reviewer said, well, so what? This is just genes, no big deal. Like everybody can create these plots. And I'm like, but we did a lot of work for this, right? So I thought, well, you know what? We need to do something to validate it. And what we need is basically some cell work to validate the signature. So we came up, we collaborated with a group in the UK that I work with to use primary cells that are myoblasts and then create myotubes. And when we knocked down 4 of the genes that we said were associated with hypertrophy, we had an effect in reducing muscle protein synthesis and it slowed down the turning on of myogenic genes. So he said, look, see, the genes that we found here are important in processes that are biologically relevant to the process of muscle growth. It only took about 18 months to do that, but by the time the reviewers were finished with us, we did get into the journal. So took a while. It worked. There's the myofibrillar synthetic response over a week of resistance training, a week of unilateral lower limb suspension. When you look at the change in lean muscle mass, you go up by about 5% with resistance training, you go down by about the same amount. We thought initially going into this, if you were this special person up here, so you were a 12% responder, maybe you were a big atrophier, but you weren't. Didn't matter. No relationship between the two. We thought that was a remodeling response, but it wasn't. And you end up creating these types of plots, protein-protein interactions, where we looked at the interaction with age, a direction with insulin sensitivity, and in our HIPAP model. And we came up looking at proteins, and LAMPTOR is a lysosomally associated protein that is part of the mTOR complex. And if you know anything about mTOR, it makes some sense that this protein would sort of come out. We discovered a lot with this study, and it was really, Tanner and the bioinformaticists that we work with in this project taught me a lot about how we are going to do a lot of science that we're going to do moving forward. Because we've worked too hard with these human studies not to give them sort of top billing. So we go on that one. Ribosomal content, translation efficiency, proteome, epigenetics, the microbiome, which apparently is responsible for everything these days. Not to be too jaded, but I hear about it a lot. Long non-coding. These are all things that we're looking at and could definitely be involved in the response. So the last part, I wanted to talk about is it's sort of this idea that when we talk about higher and lower responders, and this is Sophie Jonice and James McHenry, we think that, if you're a low quartile or this guy right here or this girl right here, you can probably creep up into this quartile with a little bit of extra work. But we don't think you're ever going to become this person or this person. The analogy, as my vet friends tell me, is you'll never make a racehorse out of a nag. So you can train all you want. And if you're this person, you're kind of destined to be that person. Doesn't mean it's a bad idea, because the health benefits are numerous. And that's kind of the last thing I'm going to talk about. But we think that this is related to changes in endogenous or internal variables, not manipulation of anything out here. Nutrition, supplements, weightlifting programs. We don't think that that has a big effect. So we're trying to sort of push away at that. So why should you care? Okay, and this is where there's a quick nod to somebody who I cite a lot, and I use this slide a lot. And this is something that Frank said in a paper that he wrote in the Journal of Physiology. And I love putting this up in front of people. I always put Frank's picture here. I don't have the reference, I apologize. But I put it to people that I say, if there were a treatment that would lower risk and reduce symptom progression for all known chronic diseases, it works regardless of age, sex, race, or risk profile. It already has a large evidence base. Like we should do studies, but we maybe don't have to. Could save the healthcare system billions. The side effect profile, the off-target effects if you're taking drugs, right, includes a better prognosis for depression, dementia, not bad, anxiety, suicide incident. I could if all of it came in a pill, of course you take it. But exercise doesn't come in a pill, and it probably never will. We can mimic certain aspects of exercise with certain pills, but we can't do it all. And the probably dogmatic paradigm that we were taught, we would look at somebody who does resistance training, and usually it would be a big oiled up bodybuilder over here, and somebody who does aerobic training over here. And we would say, this person is fit metabolically and everything, and this guy's just big, just a big guy. And this is, never the twain shall meet in terms of the health benefits of this versus this. And I think that that's changing. And I'll give you sort of some examples. So these are the guidelines across North America. They say basically the same types of things. So you've got I can get it there. There's the Mexican, there's the US, and these are actually now an updated Canadian guidelines called the 24-hour movement guidelines. It doesn't matter. They all say the same thing. Avoid inactivity, good message. We can all agree on that. And this is what anybody, if they're out on the street, remember, they go, it's something about 150 minutes of moderate, or 150 minutes. Who has time to do 150 minutes? That's just crazy. And then they say, it says, number 3 is do more of that, because now we're seeing these papers saying the dose response has actually got it wrong, that the credible intervals are suggesting that we need to do more. And for a fact, hardly anybody does that. Well, some people do, but very few. The add-on or the caveat, or it would be good to do, is this one. There we go. Oh, and by the way, it's also beneficial to add muscle and bone strengthening activities at least twice a week. But that's kind of like a sort of a footnote, and I'll beg to differ on that one. Adults should also do muscle strengthening activities, blah, 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 blah. Major muscle groups on 2 or more days a week. This is the US. There's the Canadian. I won't torture you with my, trying to pronounce that in Spanish, but it's essentially the same thing. So 2 or more times a week. And yet when you look at I'm going all the wrong way here. Excuse me. These are the under-recognized benefits of resistance training. When you compare head to head, the glycemic regulatory benefits of resistance or aerobic training, they're the same. There's no difference. It matters if you do something, not which form of exercise you do. Age-related benefits clearly include a reduction in fall risk, reductions in mobility or disability, or progression to that, and from hospitalization or abrupt sedentarism. And we always used to talk about a paradigm of, Canadians. I thought it was a uniquely Canadian phenomenon. Older people having a bad winter. They get the flu, in January or February. They get hospitalized for about 3 to 4 days with respiratory distress. They make it out of the hospital, but they convalesce at home for about 3 to 4 weeks because it's cold outside. And, you know, if you're from the Northeast or, you know, anywhere close, you've lived our winters. And there's nothing special about where I live in Canada. It's actually warmer and we get less snow than, say, Rochester, Minnesota. So, and they're honorary Canadians. The only thing they don't do is say the word "a" at the end of each sentence. It's like, "Hey, how's she going?" And I'm like, "Hey, you know, you want to say it. It's right there, you know." But, you know, so the point is, I thought, this is a Canadian phenomenon, right? And then, COVID comes along and says, no, it's a global phenomenon. Stay at home. Don't do anything. Don't go outside. Mental health, anxiety, depression, they're all pretty impressive effects with resistance training. So the point I want to make, and I'll just use this slide sort of illustrated here, and this is a recent study, just came out, is that these are the hazard ratios for people who are doing moderate to vigorous physical activity versus a group that's doing 30 minutes or less of that a week. And this is 1 hour, 2 hours, 3 hours, 4 hours. So not a complete sort of curvilinear dose response, but something that does this. And then people who add no muscle strengthening activity or some, and you can see in all of these instances, the hazard ratio goes down. So that's at least suggestive that resistance training is imparting something that's additional to and adding to what moderate to vigorous physical activity does. So whether the mechanisms are different, or this is just that people are doing more work, I can't really answer the question. This is observational. In terms of density, this is sort of the number of people who are doing this sort of thing. You can see people who are doing 0 and no muscle strengthening, they're the biggest group by far. And there's not very many people, more people doing moderate to vigorous physical activity without any strengthening activity, and very few people actually doing, and it sort of tends to plateau. You can see that after about 3 hours a week or 4 hours a week, who wants to lift weights for 8 hours a week? That was me when I was like 18. What a waste of time, man. I had so much time on my hands. So that's the paradigm. And I think it's wrong. Like it's essentially, it's much closer to this. So there are health benefits that are more common to the two forms of exercise than there are disparate. There will always be things out here that are specific to aerobic training. You can't improve your VO2 max doing resistance training, but you can't get stronger doing aerobic training. So you got to do both. So I think that that's sort of where we're going to end up sort of pushing things with the work that we're doing. So the new paradigm is resistance training is associated with similar health benefits as aerobic training for many chronic health conditions. So if your choice is, I want to do one or the other, it's okay. Not that maybe one substitutes for the other. Both is always better, but it's better to do something than nothing. When practiced regularly, resistance training can sometimes provide a superior or unique preventive or prophylactic effect, particularly in older people. There are tasks of daily activities of living in older people that are purely power tasks. And the biggest one is getting out of a chair. And no amount of big heart, big lungs is going to help you do that. And once you can't get out of a chair, you're in full-time institutionalized care. So try and avoid that if you can. But the reverse is also true. So you want to be, insulin sensitive. You want to sort of avoid a lot of chronic metabolic diseases. You want to probably have a better handle on your body weight. Then aerobically train. But it's best to do both. Like the guidelines got it right. And not to give people who do the guidelines so much credit, but they're pretty much spot on. My proviso would be is that we not talk about, and it will be beneficial to, is that actually, I think it will be necessary to. And I particularly think that message is true in older individuals. Thanks very much for your time. I've had a really great time in Columbia. You guys have a fantastic campus. Maybe you walk around and you're like, oh, it's just Mizzou. I kind of get used to it. That next gen building, pretty damn cool. Invite me back in about 5 years when you got all kinds of stuff going on. I'd love to see it. Thanks very much.
About blue guy.
Oh, blue guy. Yeah.
So basically,
Yeah.
most exercise fluctuations in testosterone don't really matter.
Yes.
So what if you apply the hammer, then that is exogenous testosterone?
Oh, yeah.
to the blue guy?
Yeah. I mean, testosterone works. There's no question. If you get your hands on the good stuff, that sticks around, testosterone and andate or those types of forms, he'll grow muscle. I mean, that's Shelley Bassine's classic 1996 New England Journal paper. Just guys sitting around taking testosterone get bigger. There's no question. So he would get it. But the key is this is the normal physiological range of testosterone. This is where steroids are. So it's 3 standard deviations beyond the normal, diurnal, and it's up the entire time you're taking the steroids. So they work. I don't there was for a long time, steroids don't work. I'm like, you're joking. Yeah, they work. Yeah. Blue guy would grow, red guy would grow bigger. Just the way it is. James Smith. Yeah, sure. It's okay. Asking for a friend. Okay, James Smith. It's all good. No, I'm joking. Yeah.
That particular exercise, can you comment on performing each set to failure or performing only the final set to failure regarding muscle gain?
Yeah, good question. I don't think you need to go to failure on all 4 sets. That's tough. And to be fair, we're kind of taking a step back now and saying you don't need to go to absolute drop dead failure, like you're gonna just collapse at the end. If you get close to failure, so if we use what they call repetition in reserve, like I've got 1 more rep, and if I don't have a spotter, like this is going to come down and I'm stuck under the bar. You don't need to go there. So get close, and we think that that's probably enough. So you don't need to go all the way. It's neurologically challenging to push yourself into. Some people can do it, but in a previous life I could do it. Now I'm like, forget it. I go, no pain. I'm like, no pain, man. Just throw the weights down. I'm good. Exactly. Yeah. Train smarter, not harder. Yeah, exactly. Yeah. Yes, sir.
I just have one question about when you mentioned the protein, like just being a sprinkle. With this perspective to like a coma or someone that is not, and then that sprinkle is going to be a lot more important. And what's about the effect of providing amino acid to that person in coma?
Yeah.
And maybe alternatives to stimulation or something that allow them to exercise. Maybe comment on that.
Yeah, it's a good point. I mean, all of the sprinkle effect is, these are able-bodied, sort of relatively healthy individuals that are able to do all the things that, in a gym and that we think that they could do. You take somebody who's on bed rest, you take somebody with chronic mobility issues, spinal cord injured patients are an example. In those populations, there could be a much greater anabolic effect to having protein around. And if they can't voluntarily exercise, electrical stim, functional electrical stimulation, those types of things, effective. It does work. They're great questions. Harder to answer working in patient populations, but certainly worth investigating for sure.
One more question.
Hi.
Just want to ask about psychological effects.
Oh yeah.
In that factor.
Yeah.
What would you say about that?
Yeah. So I'll give you 2 parts. A lot of men, they go, aren't you afraid that people will go in and lift light weights and just not see anything? And I'm like, afraid? I'm not afraid at all. In fact, if somebody were to go into a gym and lift lighter weights, I'm happy that they're in the gym. And we were talking about this morning, Frank, and I think it's sort of an undersold message that the biggest reduction in risk of anything is when you take someone who does nothing to doing something. You want to lift light weights? You go to the gym. I'm like, are you in the gym? Yeah. Are you good with that? Yeah. I'm like, keep doing it. So that's one answer. The other answer is I think that there's a large degree of intimidation that goes on in gyms. You talk about the psychology, and I'll give you an example. We did a weight loss trial. This was a long time ago in women. And I said, you know, weight loss programs notoriously a high rate of recidivism. I would much rather that we combine this with exercise. And it's not enough to just, you know, you go into our gym at our university, the weight room's down here, and this is where the guys are, and the aerobic machines, and that's where the women are. And I'm like, we got to change that. So we're going to teach these women how to lift weights. And we collaborate with a health psychologist, and the degree of improvement in self-efficacy, self-esteem, and all of the indices in the women was amazing. And they talked about the self-confidence that they gained. And from that perspective, I've always been, you know, a huge believer in sort of trying to convince, particularly women who are around menopause and post-menopause, it's going to be strength that's going to limit the things that you're going to do, and your bone density and all of this sort of stuff. Like, you need to lift some weights. Oh, I'm not, I can't do that. And I'm like, how about light weights, like just little dumbbells? They go, sure, I could do that. I'm like, perfect. Why not? I would love to get people to the point where they don't feel so intimidated that they wouldn't go to the gym. That's a psychology question. I need to collaborate with people who are much smarter than me to figure that one out. But it's a great puzzle to unlock and sort of just demystify what it is to lift weights. And that's been part of the prescription around, it doesn't need to be complicated. It doesn't, you know, free weights, machine weights, I'm like, cares? But that's not the ethos of, you know, and you'll forgive me, the male culture around weightlifting. And it's still very heavily dominated by that sort of, you know, people with deep voice. It's a stereotype, but you get my point. And I think it needs to be stressed about the health benefits, you know, in other populations. Yeah. You're welcome.
Let's give him another round of applause.
Can I ask for somebody, could you take a picture